pen exploded in my bag.
That always sucks. Where did I put my pen? Where the heck is my pen? Here it is. Okay, we'll start now. Now, what we're having a look at this morning is something called integration by parts. Oh, who's tall in the middle? Amjad, are you tall?
No.
No, you're not.
Ahmed.
You're not. Ahmed, yeah, can you move the projector a little bit to the left, please? Thank you. A bit more. More. There we go. Perfect. Thank you. Okay, so as I was saying, what we're looking at this morning is integration by parts. And I suppose you could compare this to the product rule for differentiation. So you know that if you have a product, like f and g, you can get the derivative. F derivative g plus fg derivative. Now, it's the same idea for integrating. If you have a product, you can integrate as well using something called the product rule. So I won't be surprising you if I tell you something like, if I asked you to integrate x sine x dx, that is not going to be x squared over 2 minus cos x, right? I mean,
Yeah.
we've seen this before with the differentiation. It's not a simple, straightforward thing. So by parts, the rule can be written in different ways, and some of you might have studied it before. So I'll just write the formula down. It's all the same, but I just want to write it the few different ways, because if you studied it before, I don't know which way you've seen it. So the by parts formula can be written like this. Integrate fg derivative equals fg minus integrate f derivative g dx. Some people might have seen it using like this. U dv equals uv minus integrate v du. And some people might have seen it like this. Integrate u dv dx equals uv minus integrate v du dx. So they all mean the same thing. I'm just showing you the three different ways. I'm sure if you studied before, you would have seen it written one of these ways. So for example, when I was in school, it was written like this. The formula book, though, I think the formula book that you'll have will write it like this. And this is the way I prefer to write it because it's just the most straightforward way to write it. I'll explain how it works now. So I'll be using this notation. Might be worth noting that this is in the formula book, I think. But this is maybe how you even saw it in school. They're all the same. They're all the same. Now, the key thing to note is that you start off with the derivative on g, and in the formula it moves to f. That's really, really the main point. Okay, if you can kind of remember that, you've really remembered the formula. Alright. I think it would be good to write the three different versions down, because I don't know which book you might be using or which website you might look at. So it'd be good just to have the different forms written down. And then we'll have a look at some examples then in a moment. Come here, Michelle. Okay, you got that? No, I see people writing. Going to buy the electric scooter? What do you think? Maybe?
It's too late in the year.
Yeah. Too late.
Too late in the year.
But you can use it next year.
if you're staying in Ireland.
Nothing says professionalism like seeing a doctor go to school on an electric scooter. Like, professional.
I've seen them.
Yeah. Yes.
So, using one of my questions,
Yes.
why is the dx being written in if it's just going to be cancelled out?
Yeah, it's only for style. It's to emphasize the fact that this is a derivative. So they're all equivalent. They're all equivalent. It's just a style thing. I prefer the first one because it's just the most straightforward. Let's have a look. Can I scroll down now? Yes, guys? Yeah. So it'll only take me 2 lines to prove this formula. So the proof is quite simple. So I have fg derivative dx. I want to integrate that, and I want to prove that that's equal to fg minus integrate f derivative g dx. So the way to prove it is you differentiate everything. If you differentiate this, a derivative and an integration, come on, just about in time. Well, not really in time. What was I saying? Oh yeah, so if you differentiate this, it cancels the integration. So you're left with fg derivative. If you differentiate this, it's the product rule, which is f derivative g plus fg derivative. And if you differentiate this, what have you got? Well, the derivative and the antiderivative cancel, so you're left with f derivative g. That cancels with that, and you're left with an obviously true statement. So it wasn't even 2 lines. Oh, Mubarak, you've literally seconds to spare, and I wouldn't let you in. Come on. Seconds. All right. Now we've passed 9:15. Okay. Can I scroll down to an example? Yeah. Yeah? No? Okay. Come on, guys, what the heck is taking so long? Can I scroll down? Yeah? Yeah. Okay. So the key idea behind this technique, let's take an example. We'll say x cos x dx. The way this formula works is it tries to simplify what you need to integrate. So it can sometimes make this piece a little bit more difficult or keep it the same, but then it'll try to simplify the left piece. So you can see x is already simple enough. If we could make it even simpler, then this would become so much easier. I'll explain with an example. So you start off by calling this piece here the x, we call that f. And this piece here, the cos x, we call that g derivative. Then what you do, well, this is what I like to do, because I find that this works best with students. Make a little table, and on the top you write f and then its derivative, and then here g and its derivative. So you know that f is cos x, so what's its derivative? Minus sin x. And you also know that g's derivative is cos x, so what's the integration here? Sin x. This table with the formula, this equals fg minus integrate f derivative, which is minus sin x. Hang on. We're not awake. Nobody. Yeah, nobody.
Yeah, f is x.
I know, but no, nobody said that when I said it. Hang on. Do you know, I've drinking so much coffee, I've switched to decaf, and this is decaf, and I think there's a disadvantages to using decaf. It doesn't have the same effect in the morning as a regular coffee. Let's try that again. So what's f? X. There we go. F derivative 1. G derivative cos x, and G
Minus sign.
sin x. Good. Okay, now we're set. All right. So using the formula, this equals f g minus integrate f derivative, which is 1, g, which is sin x, isn't it? Yeah. dx. Yeah. Let me just write the formula down. F g minus integrate f derivative g dx. Can you see me just matching them all up? Yeah. Now look at what's happened. Our original problem here has now become this. Now, do you need to integrate this? No, because there's no integration here. Do you need to integrate this? Yes. However, you've made the integration problem much easier. Instead of having x cos x, you have 1 sin x. 1 sin x being, of course, the same thing as just sin x. Integrating sin x, I think we can all agree, is much easier than integrating x cos x. So this final answer now is x sin x. Integrating sin x, what do we get? Minus cos x. So minus minus?
Plus.
Oh, I should move it to the left. Now, this example is a tiny bit too easy for the exam because, as you can see, I've just done it in 2 lines. So it's a little bit too easier. So we'll do a slightly harder example next. Question? No? Got that? Yeah? Scroll down? Yeah? Okay. So look, here's a slightly harder one now. Very similar, but a little bit harder. I want to integrate x squared sin x dx. Okay, so let's make our table again. F derivative, g derivative. Okay, so what's f?
X squared.
X squared. And f derivative would be 2x. G derivative? Sin x. And so g minus cos x. Right, so according to the formula, this should simplify to f g minus integrate f derivative g, which is minus cos x. So 2 minuses will make that a plus.
Why is it minus x squared?
Sorry, did I write minus x squared?
Yeah,
Yeah, because it's fg. And g is minus cos x. Is okay? Now, the problem, although simpler, is still not solvable. I've gone from having a problem with x squared sin x to now having a problem with 2x cos x.
Have to do it again.
So yeah, you realise what this formula is doing, it's like it's chipping away at it, making it simpler each time. So if we were to use the formula again on this piece, so another table, f derivative, g derivative. Okay, so f is 2x, f derivative is 2. G derivative is cos x, and g sin x. Okay, so let's use the formula again. I'll put that in red. So plus f g minus integrate f derivative g. Now 2 sin x, I of course can just take the 2 outside. So I'll just write it here like that. in front. Now, by using this rule twice, I've changed my original x squared sine x into just simply sine x. You can kind of get a feel for what's going to happen. If this was a cubed, then I would need to use the rule 3 times. Yeah, it chips away until it's into something simple. Right, so now we can solve. Minus x squared cos x plus 2x sine x. Integrating sine is minus cos. Minus minus plus 2 cos x plus the c. Oh yes, I got your email about the visa. Come in. You got your visa sorted? Yeah. You got that? Yeah.
Sir, should we always assume that the second part of the problem is the g derivative?
Well, I'm just about to get to that. Which is the g derivative is actually a very important question, because you can make your life easier or harder by the choice you make. So we'll talk about that now in 1 sec. Okay. Can I scroll down? Can I?
Yes.
Yeah? Okay. So, as I was about to say, and Mo was asking me this too, and some of you might have seen this before or thinking about it. If I was to say integrate x sine x dx, or if I said integrate sine x x dx, they're the same thing, of course, because if you just swap a multiplication, you don't actually change anything. However, you'll discover that this is quite easy to solve and this is quite hard to solve. If you call this g derivative, it's much harder to solve. And I'll show you why. Can I scroll down? To here, is this okay? Yeah. So, let's look at this. And if we were to use the formula here, f is sine x, f derivative is cos x, g derivative is x, and g is x squared over 2. So if you were to use the formula here, it would be f g minus integrate f derivative g. F derivative g. Now what's happened? Has the integration become easier?
Hard.
No, it's become harder. Yeah. So it is important which way around you have them. And there is a way to check if you have them the right way around. So there's an abbreviation which you can use. It's a guideline for what's the correct order for having them in. So the L stands for log. If you have a log, that should always be the first on the left. Okay. I stands for inverse, meaning sine inverse, cos inverse, tan inverse. That has next priority. A stands for algebra, meaning x, x squared, x cubed, etc. T stands for trigonometry, meaning sine, cos, tan. And E stands for exponential, e power x. So you notice in the example that I did previously, this is an A and this is a T. That's the right way around. This example here, this is a T and this is an A. That's the wrong way around. In the previous example, again, this was an A and this was a T. That's the right way around. Yeah? The letters, yeah. So if you want to write this down, L stands for log, ln. Okay. I stands for inverse, sine inverse, cos inverse, tan inverse. You know, the -1. A stands for algebra, x, x squared, x cubed, etc. T stands for trigonometry, sine, cos, tan. And E stands for exponential, ex. So if you've don't think you'll remember that. You should write that down.
Sorry, E.
E stands for E. That's the hardest one of all to remember.
And the priorities from right to left.
Maybe in the Arab world, but here it's left to right.
Yeah, but,
so,
but then how come you're making f g derivative sine x in the other one then?
which one? Yeah, because when you integrate something, for example, if you have, say, an L here and a T here, like a log and a sine, that's fine, because the L should be to the left of T. But if you had something like this, a sine and a log, that's wrong. You need to swap them, because the T and the L are the wrong way around. The L should be to the left of T, see? Should keep that order. Yeah. Yes.
I'm keeping track of my questions because I don't keep track of my questions for this last episode.
Go on.
So, so the inverse and the trig could like 1 over sine inverses, or like sine inverses trig still. So.
Yeah, well, I stand for inverse trig if you want to give it a full title. So sine inverse, cos inverse, tan inverse, the inverse functions of trig. And T stands for regular trig, sine, cos, tan.
Isn't that secant, cosecant?
And secant, cosecant, cotangent as well.
Isn't that trig, or is that
Secant, cosecant, and cotan would be trig. There's no inverse in them. So just to be super clear, if anyone's confused, what would go in this one would be sine inverse, cos inverse, tan inverse. And what would go in this one would be sine, cos, tan. Okay? And technically speaking as well, if you had a 1 over sine,
yeah, that's what I was talking
yeah,
about.
that would go in the T. Yeah.
Because that's sine minus 1, you know?
Well, it's not the same as that one.
Yeah,
Yeah.
that's what confused me.
Yeah. This is arc sine as well. It's another name for it.
Yeah.
Yeah.
The other question is...
Now this is the last question.
It's fine.
Okay.
I'd rather not. Let's go. I know most I just asked you, but I still don't like
Yeah.
why did we go for the last question, the one that we just solved? Why is it sine?
Yeah, well, just to be clear, this is wrong. This is wrong. I'm trying to show you what would happen if you had it the wrong way around. It would become much harder. So you see, we have to stop now. Instead of making it easier, we've made it harder. So this is why it's important to have the letters the right way around. Now, in the exam, they not often, maybe 1 per 10 questions, they would have it the wrong way around. And you have to swap them at the beginning. And sometimes students forget to do that. And all of a sudden, they've now got themselves stuck. So a lot of times I see in the exams, before students would start the question on their exam booklet, they would just write L-I-A-T-E beside the question just to make sure it's okay. Yeah, and this is a good thing to do before you start. Yeah? Okay. Let's scroll down. Or can I scroll down? Yeah. Now, I want to give you a tricky one to try. You'll need to use the rule more than once. Okay, but I want to see if you can figure it out. It's a hard one. Now, the example I'm about to give you is it could be on the exam, but it is the most difficult type that they could ask in the exam. So if you got an understanding of this, then you're doing well. So I want to integrate EX sine x dx. Try that one. tricky, isn't it? You might have noticed something peculiar by now.
Yeah.
Yes.
It's never ending.
Yeah.
I think I can figure it out.
Not this time. Logs ain't going to save you now. You got stuck in the loop?
Yeah. What do you do now?
That's a good question. Okay, let's have a look now. So, a lot of you have noticed the problem with this is you get stuck in a loop. I hope you also notice that the first thing you should do here is swap them because they're the wrong way around. The E always comes at the end. Well, that's step one anyways. Okay. So really I'm asking you to solve this. Now, let's make our table. F derivative, G derivative. Okay, so F is sine x and its derivative is cos x. And what's nice here is this is EX and this is EX, so that's all nice and simple. So integrating sine x EX dx equals F G minus integrate F derivative, which is cos x EX. Yeah, and you think, oh, okay, no problem, I'll just use my formula again. So F derivative. So F is cos x and its derivative is minus sine x. And again, what's nice here? EX. Yeah. Okay, so let's scroll down. So integrating sine x EX dx simplifies to sine x EX minus, now we have to be careful here, so I'll use brackets, minus F G minus integrate F derivative, which is minus G. Now let's just open this bracket. Integrate sine x EX dx equals sine x EX minus cos x EX. Now triple minus, minus sine x EX dx. And those of you who have tried this, you notice now you're stuck in a loop. That's actually good, because there is a way to break out of the loop. I wonder if anyone can see how to break out of this loop. How? No. Anybody see how to break out of this loop? EX is not allowed to be taken out of this because it's not constant. Hang on, yeah? Okay, I'll give you 3 sips of coffee. Let's just sip one.
Multiply by EX.
No. One sec, yeah? No. No. What the heck? Last sip of coffee now. No. Okay. Right. The way to break out of the loop is stupidly, yeah?
The question on the side, you can take
Very good. You can take this to the other side. So now you have 2 of them. So now you get that equals that. Yeah? So what's the last thing to do here? Yeah, integrate sine x EX dx equals a half EX sine x minus a half EX cos x plus C. So this is quite simply how to break the loop. It was actually a good thing that you got back to the start, because it means by just bringing it to the left, you can solve directly, get the answer. You'll have to wait till the next class, I'm afraid. I'm sorry. So just keep hold of that question. That's the answer. Yes. Which two? This one? Yeah, cancel which ones? This guy. Cancel with this one. Yeah, because this guy, I understand, this guy is inside an integration. It can't come out of it to cancel with that, is the problem. So in other words, you need to think about it as being trapped inside the integration, unable to be taken out. Yeah. Zoom out, is it? Yeah. Can we see okay? Is that okay?
There's some more.
Even though this was a loop, it was stuck in a loop, we only had to use the formula twice. In the exam, that's usually what will happen. They usually give you a question where you need to use the formula twice, or once, but more difficult. So I'll do one more example where you need the integration once, but it's more difficult. Okay, can we scroll down? Yeah? Okay, scroll down. Right, one more example. I'll let you try it, see if you can figure it out. I want you to integrate this. Log x dx. And you can use by parts, of course. The by parts formula. Try that. I'm telling you to use by parts. Ahmed, get off the phone. You've been using it for like the last 20 minutes.
How would you know which one is F and which is G?
That's why I said it's a hard one. You need to think about what to do for the F and the G. Right, let's look at this. Does it? Well, I'm just wondering, does anyone have any ideas on how we could start it?
Yes. Yeah.
Put in a 1. Yeah. Where? To the left or to the right?
Right.
To the right. Very good, okay. This letter is L. And this one
A.
is A. Okay, I think this is good. So let's try and make our table now. F derivative, G derivative. Okay, so F is log x and F derivative? 1 over x. G derivative? 1. And G? X. So according to the formula, this should equal F G minus integrate F derivative G. Now that looks difficult until you realize something cancels here. And what's the integration of 1?
X.
So the answer is x log x minus x plus c. I've seen this in the exam once. Was answered very poorly. Maybe one student, maybe not, got it right. Nobody. I think the reason people screwed it up in the exam is because the question never said use by parts. So people were struggling with what they should do to start it. This is a common trick for some problems in integration. You can stick a 1 in and do by parts. I think the other situations are integrating tan inverse x, sine inverse x, and cos inverse x. I think these are other examples of where putting this 1 in as a trick. I'll give you a guideline for the exam, okay? If you ever get a question in the exam where they ask you to integrate one thing, like for example, log x, sine inverse x, cos inverse x, whatever. Obviously it's not substitution because there's nothing to substitute here. And obviously they didn't give you a question where you could just look this up in the formula book. So in these situations you're forced into using this trick where instead of making it one thing you have to make it two by putting in a 1. Multiplying by 1. Okay. So it's not so common on the exam. Maybe only comes up 10% of the time in past papers. But when it has come up, they've never said used by parts. So this is, I think, what confused students here. Okay, let's have a look, just make sure.
Could I ask you to do something?
You can request something, go on.
Can you do the sine one?
The sine inverse example? Yeah, I think that might be a good idea. Well, hang on,
What's the derivative of 7?
yeah, we haven't done, sorry, this one isn't going to be on your exam because we haven't done the derivative of sine inverse. We've done derivative of tan inverse, so I'll do that one. Can I scroll down?
Yeah.
Right, so let's say you want to integrate tan inverse x dx. Well, we'll just change that into integrate tan inverse x times 1 dx.
Shouldn't the 1 be before?
L-I-A.
Yeah.
Yeah, it's okay. L-I-A.
Oh,
yeah.
yeah.
F, F derivative, G, G derivative. F is tan inverse x. And F derivative we did was 1 over 1 plus x squared, or x squared plus 1, yeah. G derivative is 1 and G is x. So this equals F G minus integrate F derivative times G. 1 over 1 plus x squared times x.
Quotient.
Substitution next. No, we're integrating.
Yes.
What do I substitute in Peng?
Don't know what it is.
Let u equal,
1 plus x.
not this time, 1 plus x squared. Because the x on the top. Yeah? So, du dx equals 2x. So that means dx equals du over 2x. So now this becomes x tan inverse x minus integrate x over u du over 2x. And what happens here nicely? That cancels with that. So you're left with x tan inverse x minus a half integrate 1 over u. Well, what happens when you integrate 1 over u? What do you get? Log u. So that's x tan inverse x minus a half log u. Well, what's u? 1 plus x squared. So you see, although this looks quite simple, what's the integration of tan inverse x? The answer is quite difficult. And this is normal in integration. It's normal in integration to actually start with something simple and it integrates into something more complicated.
Why don't you just simplify the u over u?
The u over u? What do you mean? Oh, the u over u is the same as 1 over u, do you?
Scroll down a bit.
Scroll down.
So I can see.
Well,
Your head's in the
oh, you just need me to move a bit. Can you see? I think I've seen this one in the exam. I can't remember. I know I've definitely seen the log one in the exam. Yeah. Yeah, as soon as you write this down, you can try these for a few minutes. Aria, do you mind switching the light back on, please? Thank you.
Sir, for this one,
Yeah.
should we expand it?
Which one is that? Which number?
1D.
1D.
Should we expand it before we do it?
Do you know? Either way is fine.
But would it be easier to leave it as is?
I think it'd be a little neater, yeah. Yeah, yeah, yeah. Yes, about the worksheet, is it? Are you trying these now, yeah? Where's your workbook? Yeah, come up here. Can I close this? One sec, okay.
From the black high
Yeah.
school, if we're dividing
Yeah.
and we have, let's say, 3 terms like
Are you?
x, y,
Why is this the
let's say
same?
z, and all of them are
Yeah, yeah.
like all of
G
them are
and
bigger
Oh,
than
yeah,
the
it's the
other.
same.
Yeah.
Like this is
Literally
1
the
plus
same.
x squared.
Yeah, yeah, yeah.
We take, for example, 2 of them,
This is the
say
same.
that all of this is u, and then we
Oh, we
Yeah.
don't do ones as difficult as that.
No, it's not.
okay.
It's not.
But in terms of
It's not the same.
integrating, is it the
One's
same for
4 over
this?
9, one's
Would
4
this
over 8.
still be the rule?
Oh,
Do you know
Yeah.
what do you know
I
what I'm
think I
saying?
know what you're
Oh,
saying.
yeah.
But you see, we don't even concern ourselves with triples.
Mhm.
So you're saying that in school you have a technique where you group 2 of them together,
Yeah.
and the policy is you group the simpler ones. Is that what you said?
No, not necessarily. Group whichever two you like. Usually the simpler ones.
Yeah,
Because they're easier to do. Right?
yeah, but you got to. Yeah, yeah.
But with integrating, well, how would this apply?
I don't know actually because I know this works for 2 integrating, and I don't know what you have to do with 3. And I have a feeling that it might actually become quite complicated
Yeah.
because which 2 you group together
Makes
can
a big
really, it
difference.
makes a huge difference. Makes a huge difference. So I think this rule might be too simplistic of a rule for 3. But this is not something to concern ourselves with because in the exam they'll never give 3.
They
It's-
never.
They've never given 3. It's just way too difficult for this level.
I remember back in high school, the final exam.
Had 3.
No, much worse than that. So it was the last page, second question on the page. I remember there were 6 terms multiplied by each other over another like 3 or 4 terms.
Yeah.
And with e's, logs, and lens and everything. And
Yeah.
we had to integrate all that.
Yes.
And I've never known how to solve that. I don't think
If
anyone
you,
knew how
if,
to
you,
solve
if
that.
you have a copy of the question, we could do it as a tutorial sometime.
I burnt my exam when I got there.
Okay.
Because why science square? We can just do science square.
Sir?
Yeah, let me just stop this recording here.